And last week we talked about example 11, but certainly we did not finish it. So let's finish this example. And again, in this example, our objective is to determine the critical load. In fact, there are more things we can also calculate down the road. But let's get the critical load first and to see that how in the analysis of the bin columns, how is other information we can also get from this kind of analysis, and how is the buckling of bin columns different from the buckling of columns? As you already know, that buckling of columns depends on only boundary conditions. And for the buckling of bin columns, whether you have lateral loads or not, does not really affect the critical load, right? We already know that. But what is the difference? How does that affect our other analyses? That will be the focus tonight. So last week we already found the force free body diagram. We already got the governing equation. We already found the general solution. So today we will continue solving for this. This will be step 3. Now, as you know that once you have the general solution, the next step is to apply the boundary condition, right? So we're going to call boundary conditions. And boundary conditions at support A, which is when the variable x is 0, there's no deflection. That means y of 0 is 0. And if you plug in, of course, you can do the same math, because this is something we have been doing many times. But if you just follow my calculation, that means b plus 0 minus ma. And I think I use over PL. So here, this is going to be over PL over P must be 0. So that means parameter B is just MA over P. So this is the first one we found. Next, we plug in the boundary condition at support B. That means y at x equals L equals 0. And that will lead to the following expression, which is A times sine KL plus, we already know the value of B, so just plug in MA over P times cosine KL plus MA plus MB over P minus MA over P, and this whole thing must be 0. And that can also be written as, after canceling the terms and rearrange them, we can find the expression of A. I'll just give you the expression. That is simply negative of P, 1 over P times sine KL times the whole thing, which is MA times cosine KL plus MB. So this is the expression of A. Right? Now we can find. Now, what we're going to do about this analysis is with A and B, that means we have completely evaluated this function. The only unknown is only A and B, right? That means we know everything. So what we're going to do next is to look at the behavior of this curve, because this function y of x is not completely defined. In addition to the A and B, which we already found in, that they are functions of MA and MB. But in the problem that we are not provided with any values of MA and MB. So in this problem, the question about the ratios and the values and the signs of MA and B will become an important information for the behavior of buckling of this bin column. So we want to know that how does the sign and the values of MA and B affect the buckling of this bin column. So the way to look at this is you can actually calculate the slope, and also that slope will be the first order derivative, and the second order derivative will give us moment. The third order derivative will give us a shear. So we can just get those expressions ready. The first one, the first order derivative is just going to be this after plugging everything in. And that will be negative K over P sine KL times MA cosine KL plus MB. So you can see part of it is actually coefficient. This is coefficient A times K times cosine KX minus K times MB, MA over P times sine KX and plus MA plus MB divided by P. So this is the first order derivative.
Professor?
Next one is the second order derivative. Which for cosine is going to become sine. That means K squared. You can do the same math because it's just the differentiation of y with respect to x.
What about L? I think we're missing an L, the MA plus MB over PL, right?
MA plus MB, which one here?
That last term for Y prime.
You mean here? Let me see. Well, for Y,
Yeah, like you have the MA plus MB over P. I think it's supposed to be MA plus MB over PL.
you are correct. For this one here, right? And for the other one, it's also PL. Then how can we cancel this one out without this L here? Okay, you're talking about this one, right? Cassandra,
Yeah, where you have Y prime and also for part 3. Yeah, you're missing it there and then you're missing it on the bottom one too.
No, this one there's no L because here it is the X here. We're gonna put in L.
Oh, okay.
That's why it cancel out.
Okay, I thought we were just doing Y prime of X.
Yeah, so we actually cancel out, but if you want to make it complete, you should put L here for the whole thing, and this is also PL.
Oh, but at the bottom too for 4.
And the button 2.
You have MA plus MB over P there also, but it's supposed to be PL because we haven't plugged in L for X.
Correct. So here we should have PL.
Yeah.
Thank you. Okay. And we will come back to have a y double prime. So this is divided by P times sine KL times, now this time becomes sine KX. So every time you differentiate, you take a K out of this sine or cosine function. Minus K squared MA over P times cosine KX. Now this time you drop this whole thing out because there's no X dependence in here. Now what we know is that the maximum deflection, obviously, we don't know whether it occurs We don't know the location because it really depends on the ratio between AMA and MB. So what we know is that the maximum deflection depends on MA and MB. So not just the values, but also their signs. For maximum moment, as you know that maximum moment is internal moment that equals to negative EI of Y double prime. So even in the expression of Y double prime of X, there's still MA and MB, right? You still have MA here, MB here. Which means what? Which means that even the maximum moment also depends on MA and MB. So we're gonna say that means M maximum also depends on MA and MB. Also this. Now, to better understand the facts of MA and B, we're going to rewrite the expression of Y in terms of MA and MB. So how do we do that? And we're going to rearrange the terms, because when you look at the expression of Y, and we're going to take the terms associated with NA, put it in one place, and the terms associated with MB, put it in another place. So by doing that, you're going to have the expression like this. I will just give you the final result. This final result is this. So what we're going to do is this, and we will look at expression of Y of X in terms of MA and also MB. Now, if you do it with MA, you can write this by dividing everything by MB. Then you can take the MB out.
Professor, can you make that like full screen?
Like this.
We can see your desktop.
Thank you. I click on the wrong one. How about this?
It's better.
Thank you. So this write as MB times something just slightly lengthy. So the first one is MA over MB times cosine KL plus 1. And this whole thing divided by P times sine KL. And this times sine KX. And please be careful that X is not L. We don't know X, but L we know is a constant. And then this plus MA over MB, which is a ratio, divided by P, times cosine KX. Again, X is unknown.
Is that first term supposed to be negative?
Is not negative, right? Because B is MA over P. So the coefficient here, A times sine KX plus B times cosine KX. So the sign with B is positive, right? So this part is nothing but B. This is B. This part is A,